Okay, so we are now at differentiable functions. So here's the definition of the derivative of a function f at a point x naught. So it says here that the derivative of a function f at the point x naught is given by this equation. So we have f prime of x naught equals the limit of f of x naught plus h minus f of x naught divided by h as h approaches to 0, or equivalently by this equation. So f prime of x naught equals the limit of f of x minus f of x naught all over x minus x naught as x approaches x naught. So if the limit exists. We have a theorem here regarding differentiability. So we have the theorem. So any function that is differentiable at a point x naught must be continuous at that point. So the theorem says that if a function is differentiable at a certain point, we can say that the function is also continuous at that point. Okay, so let us prove the theorem. So suppose f is differentiable at x naught, then we have the limit as x approaches x naught of fx minus f of x naught all over x minus x naught, so that is equal to f prime of x naught. So here we will use the second definition of the derivative of a function. We need to show that the limit of f of x as x approaches x naught must be equal to f of x naught, since this is the definition of a continuity of a function at x naught. So recall that we need to prove that if a function is differentiable at x naught, the function is also continuous at the point x naught. So let us continue the proof. So consider limit of f of x minus f of x naught as x approaches to x naught. Then we have limit f of x minus f of x naught as x approaches x naught is equal to the limit x approaches x naught. So we have the expression f of x minus f of x naught all over x minus x naught. Then I multiply it by x minus x naught. So the trick here is just I multiply this expression by x minus x naught all over x minus x naught, since that is just equal to 1. And then after that, I will use the property of limits. So we will have this expression. Here. And then observe that this expression here is just f prime of x naught. Then times, then we evaluate this limit as x approaches x naught. So this expression will become 0. So 0 times the derivative, so any number multiplied by 0 is 0. So hence, limit of f of x as x approaches x naught equal to f of x naught. Thus, f is continuous at x naught. So end of the proof. So here are some remarks for us to be able to know that if a function is differentiable at a point x naught. So the first one, so f must be continuous at x naught. F of f must not have a sharp point at x naught, and the tangent to f at x naught must not be vertical. So here's the graph to illustrate the two remarks here. So we can say that the function is differentiable if the function must not have a sharp point at x naught. So consider this graph. So as we can see here, there's a sharp point at x equal to 1. So we know that this is continuous, but it has a sharp point. So we can say here that this is not differentiable. For this graph, so there's a this blue line here is the tangent line. So you see this vertical line, so it has a this is the vertical tangent line, and it intersects the point x equal to 1. So if we have this graph and you take the tangent line, so this tangent line, so by that we can say that this function is not differentiable at x equal to 1, although it is also continuous, right? But if we take the differentiability at this certain point, so it is not differentiable. Next comes the Rolle's theorem and the mean value theorem. So we first state the Rolle's theorem. So it says here that for a function f that is continuous on an interval, closed interval ab, and differentiable on the open interval ab, so if f of a equal to f of b, then there must exist a point c within the open interval ab such that if we take the derivative of f at c, it must be equal to 0. Straight further the Rolle's theorem, we have the graph here. So it says that for a function f that is continuous on an interval ab, so here we have the function f, so the red line or the red curve. So we see that this red curve doesn't have any gaps or holes since this is continuous. Now we have the closed interval AB. So in the figure we have this. So this is A, this is B, and then it is differentiable on the open interval AB. So within the interval AB, and f of A must equal to f of B. So here I write a blue line to indicate that the point here corresponds f of A, and for the point B we have f of B. So this point here and this point here are equal. Now, based on the Rolle's theorem, there must exist a point C within the interval in such a way that the derivative of C is equal to 0. So for this graph, we have two C here. So I indicate as C1 and C2. So C here in the interval, it should not be only one value of C. We can have many values of Z. We must remember that we need to satisfy the theorem. So for this graph, we have at least one value of C here. We know that if we take the derivative of a function at a certain point, and if it is equal to 0, then we arrive at a horizontal line. Consider this graph, another graph. We notice that the point here is the same as the point here. So I indicate here f of 1. So this is f of 1. And then this is f of 3. So f of 1 is equal to f of 3. But we notice that it is not continuous. So the red line here is the graph of the function. So it satisfies f of 1 equal to f of 3, but we notice that it is not continuous. It doesn't satisfy the Rolle's theorem. So we can conclude that there is no value C in the interval 1 to 3 such that f prime of C is equal to 0. Okay, so for the last topic, which is the mean value theorem. So it says here that for a function f that is continuous on an interval AB and differentiable on AB, there must exist a point C element of the open interval AB such that f prime of C is equal to f of B minus f of A all over B minus A. So to illustrate the theorem, consider this graph. So this red line here is the function f, and then we define an interval AB. This is A and this is B. So we know that this function is continuous and differentiable. So by the mean value theorem, there must exist a point C. So this is the point C, wherein So this term here is the derivative of the function at the point C. So in the graph here, the derivative of the function at point C is this green line. We know that the derivative is the slope of the line at that point. So this is the slope or the line which has slope f prime of C. And consider this violet purple line. So this purple line has slope f of b minus f of a all over b minus a. So the definition of a slope. So based on this graph, the slope here is equal to the slope here. So that's what the mean value theorem say. Okay, so let us consider this example 1. So we are instructed to find two intercepts of the function f is equal to x squared minus 5x plus 4 and confirm that f prime of c is equal to 0 at some point c between those intercepts. To have an overview of the graph of f, so we have here, we need to find two intercepts of the function. So based on this graph, these are the intercepts of the function f. Now, you're also instructed to confirm that there exists c between this interval. So as you can see here, the c in such a way that if we take the derivative of that point is equal, that point must be equal to 0. So this is the point C, wherein the derivative of that point of f, the derivative of f at that point is equal to 0. Okay, so let us take also this example. So it says here that show that the function f satisfies the hypothesis of the mean value theorem over the interval 0, 2 and find all values c in the interval 0, 2 at which the tangent line to the graph of f is parallel to the second line joining the points 0 f of 0 and 2 f of 2. So here's the solution. Let us first verify the assumptions of the mean value theorem. So here's the graph of y equals 1/4 x cubed plus 1. So as we can see, so we have the blue curve. We can see that it is continuous and differentiable. So in the problem, the designated interval was 0 to 2. So we have here 0 to 2. Yeah. So here. So as we can see, f of 0 is equal to 1. F of 2 equals 3. Now, if we take the derivative of the function y, we will get 3x squared all over 4. So substitute c to x, we have 3c squared all over 4. Now, by applying the mean value theorem, so substitute all the given values. So 3c squared all over 4 equals 3 minus 1 all over 2 minus 1, 0. So f of b is 3 minus f of a is 1 divided by b minus a. So we have this equation, and then solving for c, we will get plus or minus 2 over square root of 3. Now, we select c equal to 2 square root of 3 since this value is in the interval 0 to 2. So we will disregard the negative value of this. It is not in the interval 0 to 2. So the answer is this.